All right, for the next lab, we are going to use a car and ramp that is very thrilling to one of your classmates, but I'm going to explain it to all of you. It just goes on here. The car comes off, and we put as the lab says, we put it in the fifth hole. We have one weight on it, and when you let go of it, it just rolls down. And in the last lab, we probably the most error came from trying to time start to stop at the right time. So this time, we're going to use photo gates, and it says to put the first one about a centimeter in front of where it's going to go. So I'm going to put this on the diamond for 2. And then I'm going to move the second one, but I'm going to start it wherever. I will measure that later. All right, and then they get hooked up to my timer, and you have to make sure that the one that goes in A, the first one, actually gets connected to the first photo gate, otherwise things go poorly. You never get your times. Oops, that would be in trouble too. All right. Hopefully this works. Now the way this works is, let me show you quickly on the board. Okay, as it goes through the photo gate, the car has a wing on it, and it's going to move forward. As it moves forward, it's going to go through. There's a hole in the top, and it's actually red on there. The light isn't yellow, but as it goes through, just as it gets there, the light goes out. So you can see that again. The light's on. As soon as it touches it, it goes out, and then as it goes through, the light comes back on. So we can figure out the time on that. We're actually figuring out the average time, the time when the middle of the wing goes right through, because we have the total distance is 5 centimeters or 0.050 meters, and the time will tell us on the little timer thing there. So if we take 0.050 divided by whatever the seconds is, we will get meters per second when it's right in the middle. It'll be going a little bit slower when the first part gets there, a little bit faster at the end, but right in the middle is where we'll have the average, right at this mark, right where it is here, when it passes that line. And as we do that, so Colton, here is the actual setup. We have the 2 photo gates right up here that will let it time between the 2. And as the car goes down the track, those photo gates are connected to a timer down here. And if I turn it on, it has to be an interval. It'll connect here in a second, I think. There we go. And I can turn these on. If I turn on A, and I've got them in the wrong one, then it will just tell me how long it took. Oops. How long it took for that wing, that 5 centimeter, 0.05 meter wing, to go through just A. And if I click just B, it's how long it would take to go through B, how fast it's going there. So we can find the velocity at those 2. And if I click both of them, that's the time it takes to go from the center of one photo gate to the center of the other. In this lab, we're going to use just the A and the AB as we do this. and we're actually going to use a formula to find B. We aren't going to actually measure B. We're going to find what the B is, and we're going to graph it and see how well that fits on the graph with the data that we know, and see if the velocity B can be figured out from there. So I'll roll the car down, and I will measure between the photo gates, because you're going to need to know the distance between the photo gate A and the photo gate B, and you'll need to know how long it took to go through A, and you can figure out the velocity. Remember, like we did, you can back it up and see. You're just going to take whatever the time is in seconds at A and take and divide 0.050 divided by the time, and that'll give you the velocity in meters per second. It's 5 centimeters, so 0.05 and then 0, so we can get at least 2 sig figs. You're going to graph it. You're not going to be able to graph a whole lot more than 2 significant figures, so we'll probably be okay with that. All right, and the first distance I have already measured is a distance. Let me check it again, but I believe it is, yes, 5 centimeters. So you want it in meters, so in your table it'll be 0.050 meters. So let me fill this first one out, and that'll give you an idea of what we're doing. And I'll go through the whole first one with you here. So even just to start out with, I just measured, hopefully this can focus that. So in meters, the first one, the distance from clamp A to B is 0.050 meters, because it has to be in meters. It's 5 centimeters, but that's the same thing. So now I will run the car, and I have to remember to reset the timer as it goes through. Reset. Now, just from the top, I just let it go. All right, and as I did, okay, so the time at A all right, I've got to make sure I reset. I'll get back up here. I guess I was wrong. We're going to look at the time at B. We're going to calculate from the graph what A is. So I'm going to give you from A to B and then clamp B. So we're going to see how fast it's going at the bottom, and we'll use the graph to figure out A. All right, here we go. So clamp B is 0.0980 seconds. So that's to the nearest 10,000ths of a second. And then the time from A to B is 0.1392 0.2. I'll show you that information here. So we put the time from B in this column, A to B in this column, and now we can calculate, and you can just wait till the end and calculate all of these, but I'll just show you. We're going to calculate that. And we're going to take the distance, which will always be the same, 5 centimeters, which is 0.050. So 0.05 divided by the time at clamp B, 0.098. And to 2 sig figs, that's 0.51 meters per second. All right, and I will even give you one more significant digit there, 0.510. All right, those you can calculate on your own. I'm just going to go ahead and give you the readings off of here, and you can fill out your chart. And I'll have to measure each time because we need to know what that first column is, the distance from clamp A to B. So let me put it back up here. And we'll just go through and I'll give you some more data. I'm going to leave clamp A exactly where it is and just move clamp B. And then measure it as carefully as I can. Okay, so that gives me 10 centimeters, so 0.010 meters. And then I will let it go. Reset that. All right, here we go. So the first column is 0.10 meters, and then the next column from A to B is 0.2421, and for clamp B it is 0.0792. All right. Move this one again. That is 0.1515 centimeters. And so the second column is 0.3207. And through clamp B is 0.0687. Right. Okay, so that's 0.20, 20 centimeters, 0.20 meters. Set that. And we have second column, A to B is 0.3883. And through B is 0.0618. Just another set down here. That's 0.25. And you don't have to do even. I just think it's going to be easier for you if I pick even numbers. All right. Okay. A to B is 0.4562. And through B is 0.0576. A little bit here so we can see more. Point 30 meters. Okay, 0.30 meters. Here we go. Keeps moving a little bit. Hopefully I can still zoom in enough here. Yep. The tape is letting go. Every time this moves, it gets worse. Hold it for a little bit. Okay, so from A to B is 0.5105, and at just B, oops, maybe it won't hold it for very long, is 0.0529. Right. It has 0.35 meters. I have more work to do on that here in a second. I'll let you get those numbers while I work on this again. Anytime the car comes down, this jerks on it, and then it knocks the tape loose over there. I'm not sure this painter's tape is actually going to be the answer I'm looking for, but we'll give it a shot. All right, so A to B is 0.5668, and just B is 0.0491. That one works out. 0.40. Okay. Set it. Right. So from A to B, 0.6148. Just through B, 0.0471. We're going to move down quite a bit. We're going to change this up so that we get some bigger jumps here. We don't have that many more to go. So that's 0.55 meters. 0.55 meters, whoops. I guess you're gonna have to. Trust me on that one. Reset it. All right, there we go. Okay, A to B is 0.7496, and just B is 0.410. All right, and then we'll move it down. Centimeters. Choose that one. That will be. All right, that is. Did I do it right? .65 meters, 65 centimeters. All right, here we go. So A to B is 0.8346, and just B is 0.0380. Do one more. back just a little bit more. All right. Here. That's 0.8080 centimeters. Reset this. All right, here we go, under it. All right, last set. Same order. A to B is 0.9439, 0.9439, and just B is 0.0349. All right, and that should be all the information you need. Now, you're going to calculate the speed at B for each one. And then you're going to graph speed versus distance and speed versus time on the graph paper. I got to get another graph paper. Both times, the time should be on the x-axis. I mean, speed is going to be on the y, and distance is on the x, the first one, and time is on the x, the second time. And look for any patterns, and just follow the instructions, and then you're going to calculate VA. From your speed versus time graph. You're just going to read it back to the y-intercept. If I were to, okay, when we use the graph now, for the second part, you're going to do both of the speed versus distance and speed versus time. We're actually more interested in the speed versus time, so the speed will be on this side, and it'll be in meters per second, and that's the speed at clamp B. That's from the last column that you calculated, and it'll be in meters per second. And this will be the time in seconds, and that's the time from A to B. Whoops, you still can't see that. There you go. So the time in seconds, and that's the time from A to B. And you want to stretch this out as much as you can. And the way you're going to do that is you take the longest time that you have, so the greatest amount, in this case the highest number, time here, speed on that side, divided by the number of lines. And that'll tell you how much time per line going across. And you're probably going to want to pick something that's kind of rounds off. Don't round down, you have to round up. If you round down, then you're going to have points that come way out here. So if it, I have no idea what it's going to be. Well, this will be your greatest one, 0.94. So if we say the highest is 0.95 seconds, and you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48. I'm going to guess it's actually 50. Let's say it is. Then we take 0.95 divided by the 50 lines we have, and if we do 0.95 divided by 50, comes out to 0.019. So we can take 0.019 and we can round that off to 0.02. So every little line is going to be 0.02. So we start with 0, and then it's 0.02, and we can do 4, 6, 8, 10, and at this, every 5, it's going to be 0.1. Yeah. And then 1, 2, 3, 4, 5, 0.2, 1, 2, 3, 4, 5, 0.3, and make sure I was getting off a little bit there. 1, 2, 3, 4, 5. So it is actually this one where it's going to, and just go across, and that should spread it out. And you can do the same thing. Take your highest speed divided by, it looks like a square, so probably 50, and then round down to a nice even number and number up by that as well. Now you're going to get a line, and your speed versus time, it might not be perfect, but it should approximate some kind of a straight line. If you read back, extrapolate backwards to your y-intercept, your y-intercept should be VA. That's what your VA is going to be. So you're going to calculate what the time was when it went through this first photo gate up here. Is going to be that axis, and then to find the acceleration is speed divided by time, and on a graph you divide things by finding the slope. Rise over run, speed over time. Speed over time is acceleration. So pick on your graph, and I just did this, and they're not meant to be straight, but here I've got one that it goes right through one of the crosshairs, so it's easy to read, and then just pick another one that goes through, and again, I didn't use a ruler. You're going to want to use a ruler. This needs to be, and let's say it's right there. And now you do it just like you did in math. You're going to do y2 minus y1 over x2 minus x1, and that's going to give you acceleration in meters per second squared. And that's what you're going to put in the chart on here. So the VA will be your y-intercept, whatever that is. You'll put the number in here. And your A will be your slope off of your graph, and then you're going to use that to predict this VB. At these times you'll put VA in for the VA in the equation. You're going to use the equation they have right here. Use the A that you get from your slope, and then whatever this number is, the first one is 0.200. They're looking to give you 3 significant digits here, so you can give me 3 significant digits. You're not going to be able to read the y-intercept to 3, but go ahead and calculate it to 3. And then you're going to graph those back on your line at the time at 0.2 seconds. You're going to go up to whatever this predicted speed is and use a different color and put a plus sign on it. So don't put just a regular point, put a plus sign on your graph, so wherever it is at 0.2, and you're going to put a plus sign wherever it goes. You'll just put a plus sign on that, and you'll do one at 0.3 where it is, and we're going to see if the predicted amount does the equation that we're actually using is V2 equals V1 plus AT. We're just doing it for this lab. Does that actually work in practice, or is there something that changes that so it's theoretical but it doesn't actually work in the real world? We're going to see if it actually does by putting that on. We have plotted what actually happened, and now we're going to predict it using the formula and see if these plus signs, how well they match with the line that you got. And that's the questions you're going to answer. Now I can tell you that there's going to be probably a little bit of variance, because I don't know if I can get this so you can see it very well, but if I back this up, maybe you can't see it as well here. I don't know what angle is going to show you the best. They are wood and they're laminate, so they're fairly straight. I can tell you that looking down, and maybe that's the best, if I can get you to look straight down here, you can probably see that there's a little bit of a bow in the track. So it's actually going to speed up more at this part because it's bowing down like this, and then as it comes back up it'll slow down a little bit. So it's not going to be perfectly consistent as it goes down, and there is a little bit of friction. The wheels will have bearings, they roll really well, but it's not perfect, so there is going to be a little bit of discrepancy, but we're going to see how close. It shouldn't be too bad as we do it. Send me a question if you have any parts that you don't understand. Enjoy.